So a kilowatt is about the amount of power that a hair dryer uses or a coffee maker. You know, good sized appliance, but not super huge. A megawatt is 1,000 hair dryers, and a gigawatt's a million hair dryers. And to get a sense for what a gigawatt is, that's like the average output of one nuclear plant or one very, very large natural gas fired plant. Um, it's a big chunk of energy, but that's what the grid managers are looking at. They're looking at tens of gigawatts of energy power flow that they're managing by the minute. So then I'll get back into the original presentation. Here you've got an illustration of the main components in the grid. The upper right, you've got a power plant. That could be a thermal plant, it could be a solar farm, it could be a wind farm, it could be anything. It's a source of power. And then they label a transmission substation, which I would not call that a substation. That's part of the power plant. Power plants generate power in the tens of thousands of volts. And then we use transformers to step that up to hundreds of thousands of volts for long distance transmission. And the reason why we go up to hundreds of thousands of volts is because wires are sized based on their amperage capacity, not on their power capacity, which is why I threw that formula in 2 slides ago, P equals IV. If you multiply your voltage times 10, you can move 10 times as much power through the same diameter wire. And those high voltage transmission lines, you're talking some pretty heavy wires. I'm pretty sure they're steel conductors, not the best conductor in the world, but it's economical. But in order to transfer bulk power in the smallest wire you can get away with, you want to go to the highest voltage possible. So then when you get close to the point of use, you get to a power substation, and that brings the voltage back down into the tens of thousands to get to the last mile or so to the customer. If I look out at the street here, I can see power poles. They're carrying tens of thousands. And if you don't have buried power, you'll see transformers on the poles. And that's stepping that tens of thousands down to the 220 volt, 2-leg AC that we use in our homes. I see Ken nodding, so I guess some of this is getting through. I can't see all your faces. I'm not used to trying to see everybody and screen share.
It's good, Julian.
Okay, I see there are other people are smiling too. So, one more thing about transformers. If you're an energy geek like me, you might find yourself looking at these boxes. If you have buried utilities, you probably have a steel green box out close to the curb of your street. And it may be labeled with its kVA capacity as opposed to its kilowatts. And I started out with volts times amps equals watts, but what really matters, and we're not even going to remotely touch, is something called volt amps. Sol and I chatted briefly about this over the weekend and said, no way, we're not getting into reactive power. We'll just think about watts. And as my chemical engineering professor liked to joke a lot, his comment on this slide is, whenever you hear an explosion in your neighborhood, that's one of those transformer drums. You've got one less transformer and one less squirrel.
Mm-hmm.
That's typically what knocks them out. We had a squirrel out here a few weeks ago, knocked out everybody on our street. It was downstream from us. We were upstream, but the circuit breaker that tripped was upstream of us. So
Can't help but think of the National Lampoon's Christmas tree.
Right.
I'm glad I'm not the only one trying to make jokes here. So anyway, the actual grid, of course, looks nothing like this. This is radically simplified. Looks more like this. And this is showing the intercity transmission network only. Just the big power grid that connect urban areas and connect states to each other.
To me, it looks like Texas is intertwined here. Am I just not seeing it because it's kind of small?
It's a little hard to see in this image. You can pretty much tell that the east and west are not connected. They're not pretty sure there's no connection here, even though there appears to be. And the lines that they show crossing, well, in and out of Texas, those must be high voltage DC lines. And I'm not exactly sure on that.
Now, was this by design to do two separate coasts of connectivity, or did it just kind of happen?
It really just kind of happened because when we first started getting electrification, it was done by the city.
Okay.
You would have a city utility to power the city.
Right.
And as those grids started growing, they saw the need to connect cities together to form a larger grid.
Okay.
For whatever reason, Texas did not choose to connect. One issue with the interstate transmission lines is that they are regulated by the Federal Energy Regulatory Committee. I've heard some people say that Texas didn't connect to the rest of the grid because they didn't want to be told what to do by the feds. And that may or may not be the case. It may have just grown organically this way. But regardless, they're not connected to the AC grid of the rest of the country, even though it appears that they are in here. They do have high voltage DC connections, but they were nothing remotely enough to supply them back in February. So my mouse picks a good time to freeze up.
I kind of would have expected more on the West Coast, to make it more comparable to the East Coast. It looks like the West Coast doesn't have as large of as many networks essentially.
That's a population density thing, Ken.
Okay.
And again, this is only showing the intercity transmission lines.
Mm-hmm.
Actual transmission lines will actually come fairly close to you. If you're in a suburban area like we are, you're probably not more than a few miles from a 500 kilovolt transmission line. That is.
Are those typically underground, or are they up in the sky and you'd be able to point them out?
This is all overhead. It's like the big giant pylons that you see marching across the countryside.
Okay.
These big guys.
Okay.
But can't really see it in detail here. But if you're in the northern suburbs, there's a huge chunk of the interstate grid that crosses roughly from the direction of Rome across Cobb County, then Roswell, and then Gwinnett. And it's like two of those massive 3-wire transmission lines. Enough to carry several gigawatts of energy. But then it branches out from there. And as I said, you're never that far from a substation or a high voltage transmission line. If you're in the inner city, you're never more than half a mile or so from a substation. The further you get out in the country, it might be one substation per county. And it's just a matter of efficiency and economy of scale. So again, this is a simplified version. If you zoom in, it looks more like this. And if I was to zoom in even more, if you looked at Metro Atlanta, you'd just see more and more and more of this. And again, in terms of AC circuits and what brilliant folks like Sol do in designing this stuff, this is 3 AC circuits. It's mind-numbingly complex to balance it all out and have it all actually work. So that's when I like to step back and take a bigger picture. So again, each of these colors is one AC circuit. And if you're down here in Miami, you're connected to someone in eastern Montana through an awfully long chain of links, but still you're on the same circuit.
Does the power actually transfer that far?
It can.
Really?
We try not to, but when things go wrong, it does need to move several states away.
Okay.
So that's like what you mentioned before, the Tennessee Valley Authority shipping power up to New York, right?
Yes. And we can come back and look at that again to see how the market pricing is changing. Everything's working. The grid is stable. It's just the pricing is incredibly dynamic.
Hey, Julian, why switch to DC from AC to DC?
I'll get to that in a couple slides.
Okay.
So how do you manage this? There's probably 100 utilities in the Eastern Interconnect. I have no idea how many. There's a lot. So we manage it by breaking the grid up into regions. And then each region has its own grid manager, usually referred to as an independent system operator. And what they do, they're like a Wall Street trading floor, doing arbitrage of wholesale power and balancing the loads and prices, both within their jurisdiction and in their connections to the neighboring jurisdictions. So let's say, for example, we're down here in SoCo. This is owned by the Southern Company and it's all Southern Company utilities, so it's kind of a private thing. But let's say, for example, the Georgia Public Service Commission said, Georgia Power, we want you to buy 100 megawatts of wind power. We want you to add that to your portfolio. Well, we don't have much wind in Georgia, except off the coast. So Georgia Power would then need to go running up to either the Mid-Continent Independent System Operator or the Southwest Power Pool, because the wind resources are really good up here. But it's also far from the demand. So for example, for Georgia Power to buy that 100 megawatts of wind, they would have to contract with a wind energy developer in the Midwest or Southwest and enter into a contract to buy X amount of power at X price for 20 years, whatever the typical power purchase agreement is. So you're going to generate some power up here and you're going to use it down here, but how do you get it from here to here? It's all through that complex network that I showed you, but it's also that power generation needs to be managed by the Mid-Continent ISO and then sold to the adjacent ISO and then sold to Tennessee Valley Authority, borrowing everybody's power lines on the way, paying them for the use of those power lines, and finally getting down into the SoCo grid to get directed to Georgia Power.
Julian, why does Florida have so many balancing authorities or whatever?
Good question. I was looking at this last night and I said the same thing. They may have got electrified very early because of their air conditioning needs. So maybe each city really was very independent to start with, but I don't have a good answer for that.
Now, when the power presumably, say it was purchased in the Midwest and sent to the South. I'm not a science power person here, but we lose some of the power in the transmission, don't we?
Yes, and that's why we go to the highest voltage possible.
Okay, so it doesn't make much sense for power to be transferred across long distances because it's more efficient to use power as locally as possible. Is that accurate?
There is a good answer to that, and I'll get to it.
Okay.
I think it's the next slide.
Okay.
Most of these ISOs are 501c3 nonprofits. They're funded by the utilities that are within their jurisdiction, and they tend to be very transparent with their operational data. So it can be easy for an energy geek like me to see what's going on in different parts of the country.
What is an ISO?
Independent system operator.
Okay.
Anyway, so the example that I just brought up is really core to what we're working on. How do you develop renewable energy where the sources are usually distant from the power demand? You got all that wind power in the upper Midwest, but that's not where the big cities are. And in Georgia, for example, we have large solar farms in South Georgia that are mostly feeding Metro Atlanta. So transmitting over a large distance, forgot where my thought was going with that.
Well, it's obviously just less efficient, right? So we want to keep,
And it's not point to point, the electrons, the power that you generate here does not necessarily get consumed here, but they can increase their voltage, for example, and that pushes power out in all directions. And every time it hits the boundary between two ISOs, a transaction happens. So that's how the ISOs complement each other. They manage the grid within their area, and they partner with their neighboring ISOs to keep the whole thing working. And knock on wood, it's been since 2004 that we had a major grid problem. There was a power line outage that started in Ohio. It was a heat wave. We've heard about the wildfires in California getting triggered by sagging power lines because the power line is heating up so that the metal droops down and shorts out. That happened somewhere in Ohio during a heat wave. And instead of the problem being isolated, it rippled out and took out the entire Northeast. Tens of millions of people. I think it was a couple days before they got it fixed. And
so it sounds like our grid is going to need some adjustments for increasing temperatures with climate. And the Pacific Northwest right now, I did see something today like that one of their electric cars or something wasn't running, like their electric streetcar running, and they showed a picture of the power line and the cord, and it didn't look good.
And you get the gold medal of the day, Emily, for the best question and point made. Yeah, it's really fragile. It's amazing it works as well as it does. But we're constantly improving it too. In fact, in Biden's infrastructure plan, I've seen something mentioned that sounds like it's a federal overlay of all of this. Which would make a lot of sense. If you standardize procedures across the entire network, then each ISO can operate more efficiently. I'm just guessing, but I've been reading about what may be in an infrastructure bill. So again, let's get back to the issue of how do you get renewables from where they're generated to where they're used. without trying to share this really busy traffic that is networked on the whole country. This is an example of a high voltage DC transmission line. This particular example, they tried to get it approved. It's never going to get built. They met too much resistance from environmentalists in New England. And once in that part of the country, the environmental community is against you, it ain't going to get done. But I like it because it's a very interesting example of how a high voltage DC component of the grid can work. And it also shows a couple things that are also very relevant to converting the grid to renewables, which is reallocating stranded assets, old pieces of the grid that are left over when a coal plant shuts down or a nuclear plant shuts down, and repurposing those stranded assets for renewable energy. And this is something that's happening right now in real time on an ongoing basis.
Hey, Julian, do you know what the reason was for the environmental groups fighting this?
The portion in Maine would follow an existing high voltage transmission corridor, but that's all overhead wires where high voltage DC is usually buried. And if you've been to Maine, the upper part of the state is very environmentally sensitive, very natural setting. An overhead transmission line can just cross a creek or a river. But if you're going to bury a power line, then you've got to dig through that same spot. And what they don't show in this slide is there was also a connection between this county line wind that was proposed and Canada for Quebec Hydro, because Quebec has tons of hydropower. So that portion of the grid was going to be all new transmission lines cut through virgin forest. And New Englanders are a bit more protective of their forests than Southerners are, unfortunately.
How does it go through the ocean?
Buried deep sea cables.
Okay.
To move a gigawatt, which, yeah, this was about a gigawatt line, it takes 2 wires that are about 6 inches in diameter, including the insulation. And we're really good at laying undersea cable. We've been doing it for phones and fiber optic and the internet for years. A very mature technology. And one question I had on this slide before is, why go underwater when you can just go over land? Well, southern Maine and the seacoast of New Hampshire, where I grew up, and northern Massachusetts, it's all built out. You can't go digging and burying power lines under streets and highways where the overhead power line would just cross that highway. So very, very expensive to do this kind of thing in a built out area.
So Julian, is there a kind of high level explanation why it has to be underground versus the AC being overhead?
Solely, you still with us?
Hi. Yes, can you hear me?
Yeah. You want to
Hi.
field that one?
Sorry, what was the question?
Yeah, so why underground for high voltage DC?
As opposed to AC? I think because high voltage DC lines are relatively new compared to AC, which has been around for a while, I think it's more out of convenience that you generally want all the power lines underground, if preferred, rather than DC, rather than overground. But also, high voltage DC is typically 800 kV or higher, 700 and whatever kilovolts and higher. So I think they also want to minimize any potential risk of arcing and the like. You certainly don't want anything dangerous happening at extremely high voltage because it could cause a lot of issues. So if you're going to do new power lines, might as well do them all underground rather than overhead, I should say. So, but in terms of any electrical reason, I don't know of any electrical reason why you'd want it underground versus over. But certainly from an environmental or a safety reason, it is better.
Okay, thank you.
That's a great explanation.
This is Scott. I've read that in the push to try to build a national grid, that they're looking at using railroad lines, their right of way, to bury the cables right next to the tracks, and they can get right away from even abandoned railroad lines. And that's one approach that they're looking to try to piece this all together without being as environmentally intrusive. Thanks.
That's also where a lot of the long distance communication lines go along with the railroads.
That's a very good point, and the railroad corridors typically connect the areas that we want to connect.
And Carolyn now has a bill out there to use the highway right away.
Right.
I think I saw someone's post about that, yeah. Anyway, the reason I brought this up, even though the project is not going anywhere, is I got curious. I know this part of the country very well. The Maine coastline is really rugged, very environmentally sensitive. So I got curious about how they make the transition from buried on the land to buried in the ocean. And did a little research, and here is where that line would make landfall. This is in Wiscasset, Maine. There was a nuclear power plant here, and it was shut down early. It only operated for 24 years. I think it had safety issues, not to mention the New England environmentalists. So here's where there used to be a nuclear plant, drawing on that nice cold water for its cooling systems. And you can see this kind of bare patch here, which is overhead high voltage transmission lines that connected that plant to the grid itself. And the grid in that area being roughly following the coastline. So maybe 20 miles in or something. So what's left over after you decommission a nuclear power plant is the wires leading to it, a stranded asset. And this is what's called a switch yard. It's got all the switches and circuit breakers needed to connect or isolate from the grid as necessary. When you decommission a nuclear plant, there's nothing nuclear about the switch yard, so they don't dismantle it. That's just an added cost. But where the reactor building and the turbine hall were, are completely gone, returned to their natural state. And interestingly, right here, you see what looks like 4 concrete pads. That's all the spent fuel from 24 years. And that's typically what's done when nukes are shut down. The spent fuel is moved into dry cask storage, and security is just as high as an operating nuclear power plant. And these things are virtually indestructible. But until we figure out a better solution to dealing with spent nuclear fuel, it largely stays on site. Anyway, back to the transition from land to sea. Here you've got an area that was already environmentally impacted very intensively and restored to some level. But the environmental impact of now burying underground and making the transition to the ocean is going to be really minimal. Nobody wants to build a golf course or a country club down here on the water because there's a bunch of spent fuel stored there too. And it wouldn't bother me walking past a dry cask storage facility. I've actually visited one. But most people would not be comfortable with the idea. So this area, other than trying to return to nature, is essentially abandoned. So great place to put in a new piece of infrastructure using a stranded asset that's left over from the old infrastructure. And I'm not sure, no, I don't, there's, where it makes landfall in Boston, right in the harbor, they take more stranded assets. There used to be a large fossil thermal power plant in South Boston, and it's got its accompanying switch yards and substation, etc., that are all just sitting there now. So this power line makes landfall, and within the space of less than a city block, you can have a DC to AC converter, and then you tap into an existing part of the grid, namely where that fossil plant used to be. So the cool thing about this is you can take a gigawatt of power that you made up here and deliver it directly to downtown Boston. Another reason why this was not popular with people in New Hampshire and Maine. A lot of, well, I'm not sure what the correct word is, but they don't like building assets to supply Boston with power. Anyhow, moving ahead. Here's one that actually is getting built. I mentioned earlier that Quebec has abundant hydropower, ridiculous amounts. It's tens of gigawatts. I have no idea. This is going to be a high voltage DC transmission line buried in the bed of the Hudson River to go directly from the hydropower power source and pop up in Queens, pop up right out of the East River, where there used to be a huge fossil plant. So again, as with the case in Boston, you've got stranded assets there, you've got switch yards, you've got substations, and you've got connectivity to the grid right where the load is. Not sure what the capacity of this was planned for, but you can do a gigawatt, you can do 2 gigawatts. Not a big deal. The only place where it's a big deal is you see they go overland for part of the route. The reason for that is another environmental legacy issue. General Electric used to have a transformer manufacturing plant in upstate New York. So they were making pieces of the grid, transformers. They also contaminated the Hudson Riverbed with PCBs. And the decision was made to not try to clean up those PCBs, because if you even tried dredging or disturbing the riverbed, you're just going to send all that pollution downstream. So they're just leaving it there, letting silt settle on it and kind of permanently entombing it. So you can't do an underwater buried line in that area. And they jump up and use some highway right-of-ways. I forget how they patched it together.
Hey,
Julian, who's, oh, go ahead, Bob.
So what's the advantage of doing this DC versus doing AC lines? Because
it lets you completely bypass that congested AC grid. It lets you go from point A to point B without using the existing highways.
But
That and there's a much lower loss in covering that length of transmission,
okay.
like 30, 50%, something like that.
Yeah, and I had put that on a previous slide that high voltage DC is much more efficient than high voltage AC.
Okay, all right, missed that, sorry.
At least part
Julian, I'm sorry.
Sure, go ahead.
No, I was just wondering, so whose project is this? Where's the money coming from?
In the legend, it says CHPE project route. This is probably the New York utility. New York State has one utility that covers the whole state,
Okay,
and they would be the ones that have a need to buy power from Canada and deliver it to New York City.
so it's state as opposed to getting federal help.
There may be federal help. I'm really not sure.
Okay,
Dee had shared something a couple of weeks ago. I think it was from a CCL resource that had another nice illustration of the power grid. And it showed some high voltage DC lines on the West Coast.
Yeah.
That are used to transfer power from hydropower in the Northwest all the way down to Southern California or other areas south of there. So high voltage DC lines are a big part of the solution to the challenges on the grid. We need more of them. They work great.
All right.
Okay, I'm trying to remember what was next after this. If you don't have questions. Oh, yeah. Kind of the conclusion here. Apologize, my slide is kind of coming through clipped there, but this is a really busy illustration of a smart grid, the grid of the future. This is taking all of the existing infrastructure and improving it to make it more resilient, improve communications, etc. Manage distributed generation and distributed storage. It's really hard to find an image that conveys this without looking so cluttered and busy. But if you look at the top, you've got your generation plant, and again, that could be any form of power plant. You've got an illustration of the grid going around in a circle to feed these different load centers. Here's a substation, and they've got a graphic showing a battery there, which makes a lot of sense. That's a good place to put batteries. Here's some institutional user, and they're trying to illustrate energy efficiency. Whoops. Energy efficiency, solar power. I'm not sure what that box is supposed to represent. Those are all assets tied to that institutional facility. Same thing with an industrial user. They can have battery storage, etc. And then here's a neighborhood with its own solar panels and EVs plugged into the grid, and thermostats for control. And the point of this whole slide, the smart grid concept, is that these folks in the middle can communicate with everything and manage it all.
I look at that and I kind of wonder about your thoughts about some of the talk about grid security from like a ransomware or a foreign attacker, and what, I think if we're all interconnected, that's great from an environmental efficiency standard, but do you think that's something we're going to deal with in our future?
It's something we need to be prepared for.
Okay. How would we prepare for that?
Way above my pay grade.
Got it.
I'm trying to scratch the surface of this for you.
sure.
Yep.
So Julian, on, one of the things, if people selling power back to the grid from if they have solar on the roofs, is that not necessarily easily done, but is the current grid kind of set up for that, or is that one of the challenges we have?
For a local user, it's not really an issue.
Okay.
You can reduce your dependence on the grid with your solar panels and your your own batteries.
But if you were generating more solar than you, energy than you need, and pushing it back up to the utility companies.
Julian, I'm sorry.
Yeah, I've heard that's an issue for utility companies because they're set up for sending power down, but not having power coming back up.
Julian, what's a load?
It's a power demand.
A user.
Yeah, a user.
Oh, okay.
Loads is electrical engineering talk.
You turned on the hairdryer.
Thank you. I taught 6th grade science, so yeah, okay.
Well, and that raises a really important topic too, because giving grid managers control over loads, even to the level of managing your refrigerator or your dishwasher or your air conditioner, is part of the future. And it's something, we have all the elements to do it, but there's a lot of marketing to be done. Ideally, we should all have a little control panel in our home that lets us interact with grid managers and let them interact with our appliances. And there'll be a lot of pushback from that from some people.
Julian, did you get a chance to look at those proposals for managing the grid on a macro level, but on Bill Gates' breakthrough site?
I have not looked at that, no.
That's okay. I sent it to you a while ago. But it raises the question, to do this right, can we just depend on local decisions about how we manage our grid, our energy flow? The big idea that he was talking about was that, and you mentioned it earlier, that wind is in the west, and the solar's in other places. The grid assume that energy is going to be flowing in certain directions most of the time when we're mostly renewable sources.
That applies to renewable and non-renewable. But the example on the left here, the neighborhood, the subdivision that's got its own solar and its own shared storage resources, that lets you stay connected to the grid, but reduces your dependence on it.
Right.
And there was actually a neighborhood developed just northwest of the Georgia Tech campus using neighborhood level smart grid technologies. It was a townhome development. Everybody has solar in the roof. Everybody has not a Tesla Powerwall, but their own battery pack. And it's all managed as a microgrid, which would be a great opportunity to let Sol chip in if he wants, because he happens to be a regional expert on microgrids. So Sol is still there. He's unmuted.
So how many more hours do we have? Right. Yeah, no, we could talk a lot. My friend, John McDonald from GE talked about a little bit of this stuff last week. So what I can do is the next time we have a talk on, here we go, sorry. Okay. The next time we have a talk on smart grids and microgrids, I can invite everybody as well. So I was just speaking today, in fact, to one of the custodians or guardians of perhaps the most advanced microgrid in North America, and that is at the University of California, San Diego. So not Georgia Tech, unfortunately, but it is in California, like so many things. And Byron from there, he's willing to give a kind of a panel talk or something. So it's almost much of that university, which has a population of 30 to 40,000 people, is run by a microgrid, in fact. And the advantage there is that it's a mixed use thing. So you've got all sorts of things, a mixed generation, a mixed load. You've got electric vehicles, you've got solar, you've got fuel cells, you've got pretty much everything, combined heat power, cogeneration, everything. So it's the notion of you've got all of these disparate sources of energy. You've got all these different types of loads. How do you make them work together in a smart fashion? What intelligence do you need to make it all come together? And that's where a microgrid can come in handy. So in fact, one of the courses I teach at Georgia Tech, we go into that. So I've got a whole bunch of slides on that too. So that I think could be a talk for another time, is how do we lead, how do we go to this smarter grid? How do we go to an intelligent network? And also consider cybersecurity and many other things as well. So yeah, this is a multi-pronged, multifaceted topic. So beyond just the Internet of Things, beyond just combining things, orchestrating things together in a smarter fashion, there's a ton of stuff we could go into here.
Sounds like Grid 102.
Yeah, you got it.
This is grid 502.
Yeah.
Yeah, you're right.
702.
The Georgia Tech used to have a nuclear plant. Is it still functional?
A nuclear plant? I don't think it is. Yeah, I
They had a
don't know.
They had a research reactor that was shut down before the Olympics because they had security concerns.
And never brought back up, huh?
No, that was not a power plant. It was a research plant.
Oh, seriously.
Hands-on learning about nuclear.
A friend of mine is a professor of nuclear energy over there.
Nuclear is a fascinating topic. I mean, it's super controversial, but one of the topics that I follow really closely.
Yeah, he was telling me Carter was the one that shut down the nuclears. He didn't like nuclear.
Even though he was an engineer.
Carter was a Navy nuclear engineer.
Yeah.
He shut down the fuel reprocessing program because when you reprocess spent fuel, you isolate the plutonium. So now you create a risk of someone trying to get their hands on that plutonium.
Ooh.
The philosophy behind that was if you leave the plutonium mixed in with all this other horrible, nasty stuff, nobody will be able to get near it.
Yeah.
In my opinion, we need fuel reprocessing because spent fuel isn't spent. It's only like 5% burned. It's contaminated, not spent. And reprocessing removes the contaminants, but those contaminants are there and something that terrorists would love to get their hands on. So, you know, as I pointed out earlier, we're leaving the spent fuel in dry cask storage, and I'm guessing that within a generation, somebody figures out a better way to manage it. And meanwhile, it's cooling off. But nuclear could be a whole topic by itself.
Mhm.
So that's not bad. We're almost an hour.
Yeah. I don't know if our grid's getting smarter, but you made us all smarter tonight.
Yeah.
Thank you.
Agreed.
I wish I'd started my recording on time because I wanted to post this online on my Zenergy one-on-one page and
Uh-huh.
have a resource that can be shared and viewed by others, because it's great to have live questions.
Sure.
You often don't get that in an online lecture on like YouTube or something.
Well, most of the beginning was the short tutorial on electrical quantities that you did. That, that could be a small separate recording, maybe.
Yeah.
Well,
So I have a question.
go ahead.
Yeah, so I was, and again, this may have been my misconception, but that AC was a more efficient way to transmit long distance than DC. And I don't recall how I got that stuck in my head, but is there any truth to that, or is that in fact completely wrong?
Most of the reason that we started out with AC is that it's easier to change the voltage. So if you want to boost your voltage up to really high levels and then drop it back down, that
It was a-
was easier to do with AC power.
There was a big argument between Westinghouse and Edison, right, about that?
Mhm.
Yeah. Yeah, I mean, if Westinghouse had won, we'd have DC instead of AC, supposedly.
Is that what Europe has, DC?
Oh, the whole world is AC.
No,
The whole world is AC? Because I thought there was something different. Like, I mean, obviously the outlet is different in Europe, but I thought there was something, not only is the shape of the outlet different, but you have to adjust to different voltage. And
different
that,
voltage and different frequency, right? So it's 220 volts and 50 cycles instead of 60.
why do that? Like, is theirs better or different or what's? I mean, I'm really basic on my understanding of electricity.
The same as driving on the left side of the road is better.
Yeah, it's just that the local choice, who dominated at the time that they were designing these things and what did they want to do.
Okay.
Protect their market too. So, yeah.
Yeah, that's a good one too.
And there are trade-offs between 50 and 60 cycle, and there's advantages and disadvantages to each.
Hmm.
But we're mostly 60 hertz in some parts of the world of 50. Some people like plugging 220 outlets everywhere into their home. We mostly use 110 for safety.
So the practical lesson is don't plug your US hair dryer into an outlet, straight into an outlet in Europe. You will fry it.
You need a converter.
Yeah.
I have a basic level question. Don't batteries provide DC current?
Yes.
So I'm not sure where I'm going with that, but where does that fit in? Or does it fit into a grid question?
Yeah, well, if you're gonna use that battery power on the AC grid, you have to convert from DC to AC. And there are ways of doing that.
And if you're going to run a laptop or anything off of AC, it's got to be converted to DC back then.
And in a nutshell, it used to be difficult, but power electronics have improved radically in recent decades. So we can step DC voltage up or down quite easily now.
Yeah, the power converters for your laptop, you can use anywhere. Usually.
Right, you just have to have the right type of plug.
Yeah.
So I just flashed back to some real-time
Oh yeah.
energy market, and New England is about the same cost as when we started an hour ago. It's a little high, but stable. New York still pretty expensive, but they're in a bit of a heat wave, and it's going to be hotter tomorrow. It'll be even worse.
So you're focusing on the marginal cost of energy in this chart. There's a lot of stuff here. So I'm trying to.
Locational marginal pricing. This is the price for power that you did not anticipate needing. But you see, I think it was like 95 in New York City today, and you can see they're pulling in power from almost every direction. Except for New England, they're shipping power to New England.
Oh, okay. I'm beginning to figure out the chart now. Interesting.
These are mind-numbingly complex, and you can dive in as deep as you want.
Mhm.
You can get an instantaneous readout. See, most of New York's renewables is hydro. That's from Quebec. But they got a pretty good chunk from wind. 343 megawatts right now.
I have another question, and that is when Terry and I were listening to, or we're talking about, I don't know if Terry, you remember this, we were talking about Bill Gates's book.
Yeah.
And he was talking about, so say we electrify all the homes, like my house is built to have natural gas power some of the home and electricity power some of the home. What kind of updates need to happen on a smaller scale to handle, say, the electrification of a neighborhood that all of a sudden has everybody on heat pumps, electric stoves, electric dryers, and also electric cars even being plugged in and powered at home?
So what was the question exactly, Emily?
What needs to happen? Like, we're not prepared for that, are we?
We're getting there. Utilities are giving incentives for you to reduce your electric load.
Well, I think it's the other way around. So if you were to electrify your house and everybody, or not everybody, but, you know, well, I can imagine in Forsyth, everybody having an electric car. What would that do to the power demand?
And the grid, could the grid take that?
Well, and that's when it gets back to the grid managers. And if they could interact with your vehicle charger and even the power stored in your battery, that's one more resource that they have.
Okay. So it's
know-
not a total negative. There could be some upsides to having a bunch of batteries plugged in at night.
Right.
Okay.
It's complicated, but the EVs can be a really good resource for distributed storage.
Mhm.
Not just powering you up for your next drive, but interacting with the grid. And if you've got that hypothetical control panel in your home, you can prioritize things like, say, prioritize my car because I'm going to be needing it, or put a low priority in my car because I'm not going to need it for the next day. And if you put a low priority, that would tell the grid manager that they can draw down some power out of your batteries to stabilize the grid. And it can also let you pick when to charge. It's sort of like some cars have an econ versus power switch on their automatic transmission. Do I want to run my house in economy mode, or do I want full power whenever I want it? And in the economy mode, if you were leaving your home in the morning to go to the office and loading up your dishwasher and loading up a load of laundry in your washer, ideally, you're an intelligent load management system would decide when to run those things.
Will this be on the new smartphone? I mean, on the updated smartphone too?
I'm sure there'll be an app.
Yeah.
Ooh,
We have all the technology. We've got all the pieces in place. There's a lot of public education, and we'll probably see a lot of artificial intelligence to manage it all.
wow.
And there you'll have the same issues you have with any new technology.
Hmm.
But, you know, if we as power consumers can play a little bit of arbitrage and manage our load to match pricing, it should save us money while saving the utilities and grid managers a lot of hassle. They like a nice, stable, consistent load. And we're not like that.
Well, right now we don't really have any incentive. I mean, there's no incentive power-wise for me to do my laundry in the middle of the day versus late at night. Doesn't matter.
Well, and Dee, how have your electric bills been? Dee's on time of use pricing, so he's getting some real advantage out of his solar.
It's been saving me a lot of money. Let me tell you what, hold on a second. Let me look this up. What am I looking up? Okay. Oh, let me look Georgia Power, my Georgia Power, Sony app. Sony app.
A lot of businesses have a strong incentive to use less power during peak periods, particularly manufacturing plants.
This is Scott. I got an EV and converted my house to all electric. And my EMC offered me a time of use plan that is saving me money. But I've got to be careful between 3 and 8 p.m.
Yep.
in the summer.
Hmm.
Okay.
We are charged more between those hours.
Quite a bit more.
Yeah, yeah. Because we have smart meters now, and smart meters tell you exactly how much we are using, by minute. So they are, they're charging us more. Okay, usage. Home. Okay. Yes, Sunday I used 13 kilowatt hours.
Wow.
Saturday I used 8. That is net because I'm getting solar. Friday I used 10. Thursday I used 4. Apparently there was a lot of sun. Wednesday I used 2. And then Tuesday I used 10, 11. Last Sunday and last Saturday I used a lot. 21. I think that was when, no, it wasn't anyhow. But yeah, I'm talking about the past Sunday. And this is the June 19th and 20th.
So is the weekend peak there just because you're home?
We're always home. We're always home. There's no weekend. This depends on if there's it's really hot.
Oh,
and
okay.
No sun.
Okay.
I think it wasn't 19th and 20th. We had rains.
Yeah, I was going to ask if that's
Yeah.
correlated with rainy days.
Gotcha.
Yeah. And earlier that week, were like Wednesday, Thursday, Friday, I used quite a bit. And then on Tuesday, the 15th, I used 3 kilowatt hours. Monday, June 14th, 2 kilowatt hours. So yeah, sometimes they have negative.
So is that your total usage or your
My net usage
net usage
after my solar panel.
after your solar? Okay.
Great.
Gotcha. I now I understand.
How big is your home?
Like 3,600 square feet. It's brand new house, well insulated. There's only 2 of us, but when was my daughter left on Wednesday? When did she leave? Because we had my son and daughter were here that weekend that we used a lot. Oh, where was I? Yeah, the 20th and 20th. My daughter left on Wednesday, the 23rd. My son left on Sunday, the 21st. So anyhow,
Another interesting byproduct of this, and I've heard the same sort of information that you're giving us, Dee, from other people who have gone solar, is that they have much more awareness of what they're doing, right?
Mhm.
You can start to correlate your use with your behavior.
Sounds like you've got enough data for a PhD candidate there. Really?
I don't think so.
Go for it.
And I can tell you how much of what is it? How much every day of power I've got. I make my panels. Okay, today. Hold on, what am I looking at? This energy. Okay. Today I made 25.6 kilowatt hours. Yesterday, 24.6. Okay. The day before, 22 and a half. The day before 27.3.
And-
Uh,
You have a storage battery as part of the system?
no, I don't.
Okay,
That's only my next investment too.
so that power is either being used by you or it's going back on the grid?
Yes.
And Dee and I actually had started talking about how to integrate a storage system,
Hmm.
which would let him extend his solar power into the evening hours
Sure.
and not be buying power, but using your own reserves.
Hmm.
And he could also do the econ versus power mode version where if we know
Yeah,
where
the
we're
thing
at,
is, I make a lot of power in the morning and I sell it cheap, but in the afternoon, when I use it more, I'm buying it more expensive.
when you could be charging your batteries with that cheap orange power,
Yeah,
and then
Yeah.
sell it back to yourself when the grid is expensive. And you're your own grid manager then. If we could all just be grid managers, everything will be fine.
Yeah, there you go.
Everyone, I've got to take off. Enjoyed it, Julian and Saul.
Yes.
Thank you very much.
Good.
Good seeing everyone.
Yeah, good seeing you, Scott.
Same
Bye-bye.
here.
And
Thanks, Julian.
we need to somehow get the law enacted so HOAs cannot limit your solar
Oh, yeah,
power.
yeah. It's forbidden in my subdivision.
They used to be, forbidden for have satellite, and they removed that. They were able
Yeah.
to, be able to remove that. But we need to get, because of all this, we need to be able to do some kind of law that removes that,
I think we would actually make headway on that in Georgia because I think, eco people want to have it for their own ecological reasons, but there's kind of an independent streak too amongst conservatives who don't like
Yeah.
to be told what to do by their HOAs.
Yeah.
that's
And I
true.
get that. So I think there could be a broad base of people who'd be willing to
That was
support
the,
that.
That was the rallying cry of the Green Tea Party, I don't know if you remember that.
Yeah.
Debbie Dooley.
Mhm.
I haven't heard her name in a while.
No,
Whatever happened to her?
yeah, I don't know what she's doing.
She's still around.
Is she? Okay.
Oh, big time. Yeah. She brings her minions or whatever they're called to different meetings. But
Okay.
this has been really good. Thank you. I need to take 102, 109. Maybe I need to take 50, 51, 52 or whatever before 101. But thank you all very much.
Yeah, I
Well,
say
we
thank you
joked
too.
a little bit about it, but we could do a 201 and get a lot more input from Sol.
Yeah,
As you
That's
said,
very
he
it sounds like he's willing to do it.
Well, this is all good stuff to know. I mean, the
Yeah.
more you know, the more you can adjust and
Yeah,
change behavior and figure the world out. I like it.
and be able to intelligently respond to people who tell you that renewables won't work for this reason or that reason.
bingo.
Yeah.
And what good is that wind power when it's in the Midwest? Well, there's
Look
an
at
Power
answer.
can be moved.
Look at this
Yeah.
map.
That's why we got to invest in infrastructure to make it better.
Yeah.
Handle it.
Well, and again, back to Biden's plan, if he can get his infrastructure stuff prioritized, there'd be a lot of money for the grid, a lot.
Well, that'd be great.
Okay,
I
Julian,
think-
thank you very much.
We'll see y'all later.
I really enjoyed this. Yeah.
Enjoyed
Thanks,
it.
everybody.
All right.
Appreciate it.
Bye-bye.
Bye.
Good night.
Nice.